Yeah.
Yeah, so we've talked about performance, so the bandwidth performance, resolution performance. We've touched on a little bit on the reliability aspect
Mm.
because maybe you just talk. I mean, people probably know with optical encoders, you have to keep it very clean inside internally to make it work. Where that constraint isn't part of our solution. What maybe just what you've seen with the reliability and aspect of comparing the two technologies.
Yeah. So the one disadvantage for I'll start with a disadvantage for magnetic, and then I'll qualify it, of course, is we are susceptible in most configurations to an high external magnetic field. So we have a part that's a uh, differential part that can be used and will reject those external magnetic fields, but it can only be used on axis. So in other words, it has to be placed if the motor, let's say shaft, and the zoom is going to mess up my.
I
But
figured
if the motor shaft is here, we have to place the sensor right on axis with the motor shaft. Um, and maybe we'll show it. We could show a graphic or something there. But one of the things that we really like is the flexibility, mechanical flexibility of being able to place our parts inside shaft. And when you do that, we're now susceptible to external magnetic fields. And we have a number of ways that we can minimize that. And it's rarely an issue, but people don't generally carry around big neodymium chunks and hold them up to.
to
But if
electronics
you're at
or
a
your screen.
yeah, yeah, exactly. But if you're building a car and it's got magnetics in it, and you have to worry about, if someone does happen to have a neodymium magnet in their pocket, it can't cause you to veer off the road. So that's the disadvantage of magnetic angle sensing from a, let's say, robustness. That's the only one I can think of, and there may be others, but that's literally the only one I can think of right now. The disadvantage from a robustness standpoint of optical encoders is dust and dirt. So these things have these stripes that are very, very fine, especially if it's a higher resolution and a smaller encoder. And if you get a piece of dust in there and the VCSEL, the LED, can't shine the light through the little slot, it misses a count, and that can be devastating, especially in an incremental encoder where you're counting each one of those. And if there's errors, position errors, and then you integrate those over time, they integrate to infinity if you don't have an index pulse. So it can be a big deal. Now, I mentioned they make these ingress protected encoders, and so that keeps all the dirt and dust and water out. But you're talking about three figures. You're talking about multi-$100 encoders when you've got ingress protection in there.
Yeah.
So with our part, you can cover the thing in dust, you can dunk it in muddy water, whatever you want. The magnetic field remains. The only thing that you couldn't do is, throw a bunch of iron filings in there, which generally isn't an issue. So from a robustness standpoint, I think we win pretty clear. And I really am trying to be honest and think of other, but I really think that we're pretty hands down winners there.
Yeah. So those are two of the typical three trade-offs people are making when deciding on a technology, right? Space, resolution, robustness, I suppose, is a third thing, but
Yeah.
performance and size. That's like those are two common.